So yeah, so we were talking about the multi-population. I want to get into the actual API now. And we're going to do a tutorial in a little bit, but I think let's just walk through the API itself. So PySR has a scikit-learn API. So you declare these PySR regressor objects, which you then use to call model.fit. So you do this model.fit xy, and that essentially does this symbolic regression search. So here we are setting a search space. So we're saying, okay, I want plus multiplication. Those are operators that I want to allow in the search space. And we also have unary operators. We have this list. Now, PySR is very flexible. And one of the kind of complaints I had when I was using Eureka is that I wanted to define custom operators. So PySR kind of makes this a first-class feature. You can define custom operators like this. So this is Julia syntax, but you can define kind of any function there you want, so long as it goes from any float to any other float. It doesn't need to be differentiable. It can be discontinuous. It can return nans for like invalid inputs. You can define a custom operator. You can even call like external packages there if you want. You can also define custom loss functions. So this is kind of an example. Now, we do this model.fit. This is the syntax. So this x is usually a NumPy array. And you say, OK, this many rows and this many features. OK? That, and then y is a list of targets. Now, this is kind of the default way of using PySR. There's many other ways to kind of use this, but I think for many problems, you can express them in this way. So for example, if you are modeling PDEs, you simply compute derivatives of your fields, like first order, second order derivatives of your fields, and you just pass those as additional features, right? In time series, you can add delayed variables. So you do numpy.roll, you get some delayed variable, and you just add that as another feature. You can also pass a pandas data frame here, and it will kind of assign the labels, assign the right variable names to it. Okay. So this is the basic API. If you want to define a custom operator, you just pass it as a string. You see here we are defining a kind of nonlinear or nonlinear function. So we say, OK, so if x is greater than 0, return y, otherwise 0. This is just Julia syntax. So it's not like some crazy internal language I made. It's just you're passing Julia code here. Right? So you could write any valid Julia code here. If you don't know how to use Julia, just ask ChatGPT. Like, I want to put this Python into PySR as an operator. Write me the Julia version. And it does a pretty good job. A nice part about this is that custom operators, they can call external libraries. So if I have this primes.jl package that defines a mapping from integer to prime using a sequence, I can just call that in my operator, right? So I say, OK, I take this input scalar, so it's a float. I round it to the nearest integer. I pass it to the prime lookup table, and then I convert it back to a float. Now, in reality, what you'd want to do here is check, like, is I between 1 and 1,000, otherwise return nan. So it's not like computing primes, but yeah, I mean, this works, which is it's useful. Now, another thing that was highly requested by people is dimensional analysis. So if you want your expression to be dimensionally correct, you can pass x units and y units here. So you can say, OK, I know the first variable is kilometers per hour, then it's constant. The speed of light is kind of the unit, and then kilopascals, and the y unit is seconds. You just define that, and it will only find expressions that are valid for these units. You can also, as I mentioned earlier, define a custom loss. So the new API for this is you write element-wise loss to specify, like, this function takes an x and y variable, so predicted target, and this is the scalar it returns. So you can define kind of any nonlinear function you want here. So this is element-wise, but you can also define a whole loss function if you want, like, I don't know, like Pearson correlation coefficient or whatever. But this is element-wise summed loss function. Okay, now this is another feature that I really wanted, and I finally figured out a way to add it. It's called a template expression. This is if you want to fix a functional form and evolve within that functional form. So here what we're doing is we're saying, I know that my expression is going to look like this. It's going to be some function f of xy minus sine of g of z. But I don't know what f is, I don't know what g is. So this is like my template, and I want it to find f and g that go in the template. So it's almost like you are, this is kind of where PySR kind of looks more like PyTorch, in that you are, you have this flexibility to set up this forward model and define different, instead of like modules, you're defining different expressions that are kind of evolved. So in this example, let me see. Okay, so this is the Julia side. This is the Julia back, and you don't have to worry about this. Basically, what we're doing is we're specifying a functional form f of x times sine of g y z, and then we're going to evolve it. I'm just going to play this, blah, blah, blah. Okay. So let's say that this is our expression. Okay, this is what we want to find, and we know that, we know it's f of x times sine of g y z. Okay, so we write this as our structure. And you see so this is what the actual output looks like. You see it's finding this Pareto front where it has multiple expression components, right? So it finds this f and this g. And what you see here is the TensorBoard output. So if you're like logging the output, this is like the min loss of all the expressions, and this is something called the Pareto volume. It's just like a summary statistic of the expression. Okay. Now, the cool part about template expressions, well, another cool thing, I think they're cool, is that you can pass any Julia code you want. So this forward model, it's really like PyTorch in that you can just write any code you want in the forward model that uses these expressions to do something. So here what I'm doing is I've got variables x and y. I want to find two expressions, expression f and expression g, such that my forward pass starts at x and then iteratively evaluates, out plus equals f of out y. Okay, so I'm evaluating this expression multiple times on its own output, right? I don't know, maybe I could write this. Let me see. Here's one. Okay. So this looks like, I have this out equals x, and then I'm doing like out I. So maybe this is out 0. Out I equals out I minus 1 plus f of out I minus 1 y, right? And then the output is essentially return g of out 10. Okay, so all of this is kind of described in that forward pass. And if I give this as the expression spec, it will find an F and G that work for this and kind of evaluate as my target. Okay? So this means like it kind of gives you a big space you can represent your problems. This also lets you do vector expressions. So this is kind of something that I really wanted it for. And now the tricky thing is that in PySR, you can only pass one variable as the target. So what you do instead is you just pass extra variables in the X. And then you just kind of like compute the loss inside the template. And you see here what I'm doing is I'm computing the Y component, Y1, Y2, Y3, and they each have this shared, there's this shared piece here. And so the complexity of a template expression is going to be the summation of the individual complexities. So like complexity of F1 plus complexity of F2 plus complexity of F3 plus complexity of shared, okay? And because I have this shared sub-expression, it's going to try to put as much complexity as it can into the shared piece. Just like I think we do when we're building models. You know, it's good if there's this complexity that's shared among other models. Okay. This also means you can learn probability distributions. So just like in PyTorch, if you are fitting like heteroscedastic, regression problems, you can also do that in symbolic regression. So you can fit an expression for the mean of a Gaussian and the variance of a Gaussian. You just fit one expression for both. And then the loss would be like the negative log likelihood is what you return. So this is just the negative log likelihood for a Gaussian. Okay, now one other thing is that you can also define parameters inside a template. So if you want to, say, fix the functional form as, I don't know, like f of x, but maybe you don't have like multiplication addition inside your search space, you can instead just write it explicitly. So I'm defining this parameter, so parameter 1, parameter 2, and as it searches for these expressions, it's going to also search for parameter 1, parameter 2 that plug into these expressions. Now, the really cool part about this is it lets you learn parametric expressions. So this is like if you want to learn a model that gets applied to different problems. So for example, if I have, let's see. It's always Wi-Fi. Am I supposed to rip these? I don't know. Okay. Here we go. Okay. For the team. Okay, I'm gonna, yeah. Okay, so if you have if your data set has 10 different categories, you want to have one model that works for all 10 categories, but you know that there's going to be slightly different parameters for each category, you can use this approach. So what it might look like is cosine of, I don't know, x plus 2.1y minus alpha I. Maybe this is your model. And then alpha I depends on the class. And so it's going to learn on class I. And so this template is essentially going to learn an alpha for every class. And so this is if you want to learn a basis function, or you want to learn a model, and you think okay, I want one model, but I want slightly different parameters for every instantiation. this is kind of what you would do. Okay, last cool feature is derivatives. You can also evaluate symbolic derivatives inside the template. So here what I'm doing is I'm saying, okay, I want expression f, I have a variable x. Now, my output is going to be f prime of x plus f of x. So this guy, df equals d of f comma 1, takes derivative with respect to the first argument. Okay? And then I evaluate that at x, and I add that to f of x. So this is computing f prime of x plus f of x. And this lets us do crazy things like this. So here, we want to do, the laziest derivative, or the laziest integral imaginable. So does anybody know the integral of this? Anybody that good at integrals? I don't know, but we can evolve it. We can evolve the integral. So what we're going to do is we are going to evaluate the integrand. So that's this guy, 1 divided by x squared times x squared minus 1. Okay, this is the old API. Sorry, I didn't update this. But I mean, this now looks like this. Like you could just do df of x. Essentially, what I want to show you is that all you have to do is pass the integrand sampled and just like define that as the forward model. And what you get as the output is the integral. Okay. There we go. So this is the integral, right? We evolved the integral because our forward model is the derivative of f, right? And so we're comparing the derivative of this guy to the integrand. And so this gives us a way of like evolving integrals. So you could see like there could be many different applications of this. Like you have some PDE that you want to find a symbolic solution for. This kind of gives you a way to do that because you could just do the, kind of evaluate like a PDE loss in the template. Yeah, this is just confusing. I mean, it's just like combine everything. We'll do examples. Don't worry. I don't even want to show that. It's just hackable. That's all I want to emphasize. It's like you can evolve expressions on strings, which I don't know why you would, but you could. And you see, it's like evolving like little strings to compare against some target strings. I don't know, like maybe you want to crack some code or something. I don't know, but it's highly customizable. Is my main point. Okay, I'm going to skip all of this. We can actually do tutorials. Blah blah blah. Yeah, maybe we could come back to that later. But tutorial time. Okay, so if you go to this link, we can go through a Colab tutorial. Now, this is a Google Colab notebook, but you can just run this locally if you want. Actually, the Colab CPUs are actually pretty weak. So if you have Python set up and you feel comfortable with it, you can just like download it and run locally. But the Colab one will work because it has everything set up. Okay. Okay, so yeah, so I got my Colab is pimped out. Got my cats, my corgis. Okay, so this tutorial walks through the basics of what? Let me just copy it there. Dear. Did I? Oh, that has the Wi-Fi on it. I didn't know what he was doing. Okay. Yeah, if you want the cats, I think they are. Where are they? This is the stuff that matters. I think it's. Oh yeah, runtime. I don't know. It's somewhere in settings. Okay, so in this tutorial, we are going to look at the basics of PySR. So the first example we'll do is we'll just like set up like a simple rediscovery. So let's say we have this data set of 100 rows, 5 features each, distributed with Gaussian, with variance of 2, standard deviation 2, and we want to rediscover this expression, okay? I think mine crashed, one sec. Start session. Okay, so I'm hoping everybody has the link. So the first thing you do is pip install PySR. This will set up, so PySR will kind of automatically install Julia for you. So you don't have to really worry about that. You just import PySR. In the first import, it's going to install Julia, install all the Julia dependencies. The first import might take a while as it needs to set everything up. But hopefully it's not too bad. Okay. Do all our imports. Okay. So this is our data set. We want to rediscover 2.5 times cosine of x3 plus x0 squared minus 2. Okay. Now we set up our PySR regressor, and we're going to set up, okay, I think for my problem, like plus multiplication makes sense, and the unary operators maybe cosine, exponent, sine makes sense. We're going to run it for 30 steps. Now, if you're running this for like an actual scientific problem, you might want to just like make this as high as possible, because genetic algorithms, they don't really converge because of they're not really like a nice, traditional machine learning algorithm. You can just like run them for longer, and maybe they'll discover like a new space of your trees. Like if you think about it, we are kind of like, humans are like a minima. Well, I don't know. That's maybe. Yeah, I mean, humans are a point in the evolutionary search space, technically, and I don't know if we're converged yet. So, yeah. Okay, so we run this. It's going to start compiling the Julia backend and starting up the search. So the first time it runs, it's going to take a little bit longer, because so Julia is a just-in-time compiled language. So it actually compiles as it runs the first time. It's a bit like Numba, if you've ever used that, or JAX. Okay, and we see our first expressions. And it finished too fast. Okay. So what we see here, as it runs the search, is the Pareto front. This is the current Pareto front of expressions. This one is the simplest, right? Complexity 1 gets this loss, this score, and this expression. And this is the most complex one with the best loss. Now, the score column is literally just the drop. So I mentioned this earlier, like how do you choose the best expression from the Pareto front? The score is basically like the derivative of the log loss with respect to complexity. So you can kind of use it as a metric for like, oh yeah, this is the correct expression because the score is high, but you shouldn't use this as the final criteria because it's purely heuristic, okay? So as the search runs, you'll see the Pareto front update. And so this is the final one. And then we get this pandas data frame output. Right, so we can run this, and this is our output. Now this is, so it stores the output equations in a pandas data frame. So if you want to look at it, you can go this, pandas data frame, okay. And these are our equations, right? So I can see my list, and okay. Model. Okay. Now, there's a bunch of different kind of helper functions. So model.sympy is going to take the expression with the highest score and convert it to sympy and give you that back. So if you want to do like other symbolic manipulations, I don't know, maybe you want to do like simplify, you can do that. And I get the simplified expression. You can also get the LaTeX version of it. So this one is like a little bit complex. I don't know why. And you can even get the LaTeX table. And this gives you like a full LaTeX table if you want to put the expressions in a paper. Okay. And so it found, like, it basically just found the right expression, right? Not too unexpected. It did have the correct operators. So now let's do an example with noise. This is going to be a bit harder. We are going to sample sigma. So this is like the noise standard deviation between 0.1 and 5. And then sample noise. So this should be like a curly n. And add that to an expression. Okay, so we're looking for this expression. And this is like, there's like a heavy noise there. Okay, so let's look at the data set. This is what we're dealing with, okay? And we want to fit this. So let's see if PySR can do this. Now, if you do know the magnitude of the noise, you can define it as like a weights that you pass to the fit. If you want to weight specific data points, which we do here. And we're also going to define a custom loss function that is weighted. So this is my custom loss function with predicted target weight. And we're going to weight the L1 loss, so the absolute error. So this is the thing it's going to try to minimize, right? And we're going to give it plus multiplication and then cosine as the operators to use. Okay. And see if we get similar results. So if you run this on your laptop, it's actually surprisingly much faster than Colab. I don't know what CPUs they're attaching to Colab, but they're really slow. Yeah. Mm-hmm. So some of it is like numerical precision issues. So because it's the default precision is 32-bit, and sometimes, simply due to the weirdness of floating point precision, it could just potentially like add another constant because it helps it get like a little bit of better loss. Other times it just like didn't find it. It just like didn't converge for whatever reason. Like maybe you run it longer, it'll work. Yeah. Okay. So it found this, and this actually looks like the correct expression, which is good. So even though it's highly noisy, it found the right expression. So what we're doing here is we're just like manually picking an equation with pandas. Okay. Let's look at the fit, right? So that's nice. So this is the original data set and then our predictions, and it gives us this smooth loss term. And if we look at the full equation list, let me just print this out. I mean, so you can see there are expressions that are actually more complex in the Pareto front. So these ones actually get better loss, right? But that's because they've kind of overfit to the noise a little bit. So this is where the score columns comes in use, because it's going to use the score, which is it's kind of like a best loss per complexity, like the pound for pound best expression, right? So this is kind of, for the complexity, this is like the best expression, even though this one is technically more accurate. And when you do the model.fit and then the model.predict, it's going to use that expression that it found with the best model selection. Okay. Yeah. Yeah. Yes. So I think the easiest way to do that is just filter it like this. So maybe I want to, I don't know, maybe I'll do model.equations dot loss plus 0.01. Oh yeah, there's this feature of Google Colab too. I don't know. Yeah, okay, so .idx, I think it's .idx min. So if I define this as my score, for example, and I compute the best index based on that score, actually, I guess this should be, yeah, I mean, this is like the negative. That is the score, and then it would be IDX max. And then this would be according to my loss, my custom score, this is the best expression, which happens to be also the right one. Yeah. But I should also say the scoring function doesn't influence the search. It's just kind of like a post-processing, how do I select an equation from the Pareto front? Okay. Yeah. Okay. So maybe at this time I'll let people like work through it a bit, and then for like 30 minutes or so, or less or more, and I'll come around and like help people.